continue our discussion of forces and objects undergoing motion due to the influence of those forces. In this next lecture, we're going to try and learn a little bit more about force diagrams and how to apply them to the equations involved with Newton's second law. So we're going to put all of that together. We're also going to learn about Newton's third law and how it pertains to force problems that we might be working with. So the first part that we want to discuss are force equations. And as we do that, we're going to consider objects to be point particles as opposed to extended bodies. So when I talk about a brick on a table, I'm really talking about a point, usually the center of mass of that brick, but it doesn't really matter. We're just going to look at all the forces as if they're acting at that one single point. Then recall from the last lecture or two the whole concept of superposition of forces. The net force acting on an object is equal to the sum of all the vector forces that are acting on that object, as if they were all acting at one location. Now later on, we'll look at extended bodies because then they're going to undergo rotation. But that's down the road yet. So right now we're going to consider all of our objects to be point objects. So even if I draw a brick sitting on a table or a book on a table as an extended body, I'm only going to be considering the object as a point object. So if a force is acting over here, it might as well be acting over there. It doesn't really matter. Now there are some objects that will be in equilibrium, and equilibrium comes in two styles. There's static equilibrium. In the case of static equilibrium, the object is not moving and it's not going to move. The net force is equal to zero. This is a body at rest remaining at rest. In dynamic equilibrium, the net force is still equal to zero. The whole idea of equilibrium is that you have a net force of zero. So in dynamic equilibrium, the body still has a net force of zero. However, it is undergoing motion. But keep in mind, if the net force is equal to zero, according to Newton's first law, the body will remain in motion, moving with a constant velocity. So the acceleration in both scenarios is equal to zero. But in the case of dynamic equilibrium, the velocity is not equal to zero. But in the case of static equilibrium, it is. We'll generally be looking at accelerating objects. Objects in equilibrium are fairly simple and they're a good place to start. But accelerating objects will be the majority of our discussion. So let's examine the book on the table again. Recall from the last lecture that there's a normal force acting on the book on the table, and there's a gravitational force acting on the book on the table. So I can write this as a normal force, and that normal force is going to be due to the table, and it's going to be acting on the book. Alright, so that's the same as we had last go-round. And then there's a gravitational force. I'm just going to label that as gravity, and that is due to the earth, and that is also acting on the book. And those were the only two forces acting on the book. So at this point I want to put in an x and a y axis, and I'm just going to choose a standard xy axis. There are no forces in the x direction, so when I go to write the sum of the forces in the x direction, there aren't any. So there's nothing over here. So this must equal m times the acceleration in the x direction. And since the mass of the book is not zero, the acceleration in the x direction must be zero. In the y direction, however, there are forces. So notice the way I write this. I talk about the sum of the forces in the x, and then on the left-hand side of the equal sign, I'm going to put all the forces that are in the force diagram. Of course, in this case, there are no x forces in the force diagram. So keep that in mind because that's going to become important later on. The left-hand side of the equal sign will be all of the force diagram forces. So the force diagram forces go on the left-hand side of the equal sign. So there are two force diagram forces in the y direction. There's F sub n, the normal force, and there's also an mg. Now I put minus mg because it's in the negative y direction. My axes show the y-axis is up and positive. Then the right-hand side is always the mass times the acceleration in that particular direction. In this case, that's the y direction. Now the book is just sitting on the table. So this is an object at rest and it's remaining at rest. And in that scenario, the y acceleration will be zero. And so Fn minus mg is also equal to zero. Now since F normal minus weight is equal to zero, then it must be that F normal is equal to mg. Now don't get that in your head that that's always the case. There are many, many cases where the normal force is not equal to the weight. This just happens to be one case where that is true. So keeping in mind the book on the table, the weight and the normal force were the same. Now this is really important because we want to talk a little bit about the concept of weightlessness. If we talk about weightlessness, the only way to truly be weightless is to be pretty much infinitely far away from any object with mass, or at least in a situation where all of the forces due to gravity cancel out. And that's pretty rare. We'll talk more about that in later chapters, but not right now. So when we talk about a weightless environment, for example, on the space shuttle or in the International Space Station, that really is not truly a weightless environment. What it really is an environment without a normal force. So let's take a simple everyday example. Well, maybe not an everyday example. Let's take a simple example. Imagine, if you will, that you're standing on a scale in an elevator. And if you have the opportunity, this is something worth doing. If you stand on the scale in the elevator, the scale will read your weight. So what the scale is measuring, theoretically, is your weight. And in fact, it is reading your weight at that moment. But if you now take that same elevator and you push the up button, what you're going to find happening is, as you start at rest and you begin to move upward, your weight on the scale is going to increase. Now what's really happening is your normal force is increased. So what a scale really reads is a normal force. In the case of a spring scale, like you might use to weigh a fish that you've caught, the spring scale doesn't measure the weight of the fish. It really, in fact, measures the tension in the string that's holding the fish, or the rope, whatever that might be. So a spring scale like that measures tension. A normal force is measured by a bathroom type of scale. So a weightless environment like you have on the space shuttle or on the International Space Station really is an environment without normal forces. So let's take a look at this example of a person in an elevator. So let's assume I have a bathroom scale on the floor of the elevator, and the person is standing on that bathroom scale. Now if I examine the forces acting on the person, there's a gravitational force mg that's down, and there's a normal force due to the scale acting up. So I'm not going to write this out, but mg is the gravitational force due to the Earth acting on the person, and F normal is a normal force due to the scale acting on the person. Now according to Newton's second law, the sum of the forces in the y direction would be F normal minus mg equals m times a in the y direction. Now if the elevator is not moving, then the acceleration in the y direction is equal to 0. So this is true if there is no y acceleration. Now that could be in a situation where the elevator is standing still, there's no y acceleration, or it could be a situation where the elevator is moving up or down with a constant velocity. So v sub y is equal to 0, or v sub y is just equal to some constant value. So if you push a button for the 10th floor and you're on the first floor, the elevator will generally reach a constant velocity fairly quickly, and so the scale is going to read your weight. So in this scenario where you have constant velocity or 0 velocity, then the normal force minus mg is equal to 0, and so the normal force is equal to your weight, and the scale is going to read exactly what you think it should. But if you push the button to go up, then in order to go up there's going to be an acceleration in the positive y direction. Now in this scenario, Fn minus mg is equal to m times a, where a is the y acceleration. And so the normal force is equal to ma plus mg. So notice the scale is going to read more than your weight, because it's going to equal the mass times the acceleration that you have plus the weight that you have. Now again, this occurs when the acceleration of the elevator is up. That will occur in two different scenarios. Scenario number one is when you're not moving and you push the elevator to go up. In that case, your acceleration will be positive y. But there's another scenario. When you're moving down and you reach the floor that you want to be on, keep in mind in that scenario your velocity is down and you're going to go to 0. So the change in velocity is 0 minus a negative v, because you're going down, so your velocity is negative, and so v final is 0 minus v initial, which is negative v, and so that's equal to positive v. It's a positive value, and so your acceleration when you get to that floor beneath you is going to be positive. And again, the scale will read a value larger than your weight. In a similar situation, while you get to the floor that you're moving to in the upward direction, the velocity of the elevator is up, and you get to a velocity of 0. So in that case, final velocity is 0, initial velocity is some positive value v, and this is less than 0. So in that case, the acceleration is negative. So if I have a negative acceleration, then my force equation becomes F normal minus mg equals m times a, but a is negative. And so F normal equals mg minus ma. So the normal force is less than your weight. And so if you weigh 150 pounds, when you reach that negative acceleration, and that's getting to the floor above you, or being at a high floor and pushing the button to go down, then the elevator also accelerates down. In both of those scenarios, the scale will read a value less than your weight. So I want you to try this or think about it, really get a good grasp of what's going on. By the way, it's worth noting that I will do my best to put all of my acceleration vectors in red, all of my force vectors in blue, and my velocity vectors would generally be green, but not always. So let's write out the force equations for the blocks that we had in the previous lecture. So again, you had block 1 hanging over the side and block 2 up on top of a table. So when I look at block number 1, there's a downward force of m1g and an upward force of t. T is the tension due to the string acting on block 1. m1g is the weight due to the earth acting on block 1. I have an x-axis to the right and a y-axis up. And so in this scenario, the sum of the forces in the y direction, because there are no forces in the x direction, would be t minus m1g equals m1 times a. Now if I look at this scenario, unless there's something pulling on block number 2, which there isn't, in this scenario we can count on the acceleration for block number 1 to be down and the acceleration for block number 2 to be to the right. And again, since they're connected by a single piece of string going over a pulley, the acceleration of block number 1 and the acceleration of block number 2 must have magnitudes that are equal. Well, given that scenario, then, m1a is actually pointing down. And so I'm going to want a minus sign in front of that. So I can rewrite this equation as t minus m1g equals minus m1a. Now don't put a negative sign in for a. The negative sign for a is already built in, so you don't want to put it in there twice. So there's an equation for block number 1. I want to keep that in mind. Now if I talk about block number 2, I know there's a tension to the right. I know there is a normal force due to the table acting on block 2. And I know there's a gravitational force due to the earth acting on block 2. T is a tension due to the string acting on block 2. So I'll put my x-axis to the right and my y-axis up, and I know my acceleration is to the right. So the sum of the forces in the x direction, I only have one, and that's t. So t must equal m2 times a. And when I look at the sum of the forces in the y direction, I get F normal minus m2 times g equals m2 times a in the y direction, but that's 0 because there is no acceleration up and down. And so this yields one important equation, and that's right there, and that's t. So you'll notice I have two equations. I have t equals m2a, and from the previous slide I had t minus m1g equals minus m1a. So there are my two equations. If I know my masses and I know gravity, the unknowns in this set of two equations would be t and a. Now we've already discussed a being the same for both blocks, at least in magnitude, but what about t? In general, when we work a problem like this, we'll talk about a massless rope. or a massless, frictionless pulley. Now because the rope is massless, if I take a look at a little piece of that rope, say right there, and I analyze that little piece of that rope, then that little piece of rope has a force in this direction, let's call it T to the right, and a force in that direction, let's call it T to the left. So when I examine the sum of the forces on that piece of rope, I find out that T right minus T left equals the mass of the rope times the acceleration of the rope. Now that piece of rope is definitely accelerating, has the same acceleration as block 1 and block 2. However, if it's a massless rope, this term goes to 0. Even though there is an acceleration, the mass of the rope is 0, or that piece of the rope. And so T left and T right must be the same, which means no matter where I choose that little piece of rope, I'm going to end up with the tension in one direction equaling the tension in the other. So the tension in the rope, as long as it's massless, will be the same everywhere along that rope. Now if I'm using a piece of cable or a piece of chain, all bets are off because those have mass. So I have a system of two equations and two unknowns, and I can solve that. And I'm going to let you do the algebra for that.